All right, I think we got the technical pieces put together, and we'll go ahead and turn it over to you, Todd. Thanks for your patience.
Couple years looking at UAVs to do temporal and landscape level vegetation modeling in conjunction with BLM. So first, I'd like to thank all the partners in this, BLM support from John Carlson, Colin Dovichin, Jason Sprung, Mike Harper, and Jennifer Harper, and all the AIM field crews, David Wood for sort of coming up with the main concept for this, and Kevin Hopp for assisting last year with a bunch of the flights. So the two projects are basically a time series analysis that we did at 2 BLM mesonet sites. These are basically climatological stations, so they have soil temperature, soil moisture, precip data spread across the landscape. We looked at 2 in southwest Montana, Argenta, where we were able to fly 9 flights over the growing season in 2018. Virginia City, we had 7 flights. And then last year, we sort of used what we learned from those flights and moved us to more of a broad landscape level, looking at different sagebrush habitats across 3 different field offices. So we ended up flying 16 flights in the South Dakota, Billings, and Dillon field offices for a total of 48 sites covered last year. And these flights were flown in conjunction with BLM's AIM survey data, so their inventory, assessment, and monitoring protocols. They have field crews on the ground, and we were able to fly these either immediately following or right before they conducted their field surveys. So for our time series flights, we had multiple flights across a growing season trying to look at how the heterogeneity that we see in MODIS and Landsat pixels is influenced by different functional groups on the ground. So we're looking at main objectives of looking at the phenological signals between the remote sensing approaches, and especially within functional groups, quantifying how the NDVI of functional groups changes across the growing season. For our landscape level flights, we were looking at the ability to sort of implement a BLM or a UAV component to the BLM AIM surveys on more of a programmatic level. And so our main objectives here were to compare our vegetation classifications that we're seeing from the UAV with what the field crews are seeing, and then to derive habitat metrics that can be transferred up to Landsat-based models that BLM uses to look at rangeland health. And so this project's still ongoing, so here's just a kind of flow chart of where we are at. So we've got all the data collected, processed, figuring out how to match our data to the BLM survey points, how to do veg height, and then with their, both just in our imagery, but how to compare that to what BLM is getting, vegetation classification. We have some approaches developed, but we're still working on that, and then have not yet got to any of the Landsat or MODIS-based comparisons. So our data collection was basically flying both the ricoh and MicaSense cameras on a 300 by 300 meter grid, so that would be 100 Landsat pixels to our flight speeds and altitudes. Had a ground sample resolution of 1.5 centimeters for the ricoh and 3 for the MicaSense. For total time on site, we were able to knock out each site in about 1.5 to 2.5 hours, depending on how much additional hiking there was and how close you could get to the site. So that's about the same amount of time as a BLM AIM survey crew is on the ground. So for our data processing for the temporal flights, we did a 4-dimensional structure for motion with only the MicaSense data. And so that's basically applying one structure for motion to all the data sets at once across the growing season. And then for our landscape level flights, we did a structure for motion with both the ricoh and the MicaSense images. Same approach for how to handle all of the MicaSense images, and I'll talk about that in a second. And then you add the ricoh to the processed MicaSense photos and align everything together. So what this looks like with multiple flights of MicaSense data, you basically add each MicaSense flight to its own chunk. Then you run your calibrate reflectance panels using your combined panels that PhotoScan pulls out. This gets you all of your bands together, or calibrates all of your flights as one. Then you can merge these chunks together, and then you have to unnormalize this band sensitivity, but that makes all of your MicaSense photos calibrated on the panel photos just before and after your flight, so you're not calibrating across multiple calibration photos and each flight is being calibrated correctly. Then you add in your ricoh stuff into one chunk, and then you merge, or then you align everything and then make two separate chunks for your ricoh and your MicaSense data, and then you can build all of your data products from just each individual camera, but all of your data is now aligned, all of your photos are aligned between both sensors to build all your data products. So what this looks like, so this is first from the ricoh data, and this is from the MicaSense for the same area. And so you can see especially the ground surface aligns really well. Anything with height can be slightly off just because of different camera angles. So notice the pin flags on the target that are holding it down kind of shift in the imagery depending on the camera angle. But you see really good alignment between pixels of especially the ground and low-level vegetation. And so from this, we developed a bunch of data products as well as the standard ortho. Using the ricoh, we were able to develop a false color image. You can collapse this down to a single band false color. Able to develop a NDVI layer as well as some texture metrics. So these look at relationship of nearby pixels. So it looks very similar, but when you zoom in, what you see, this is a standard deviation of a neighborhood of, I believe it was 20 cells or 10 cells. And so this is, depending on your neighborhood that you look at, it's really good at identifying edge features or internal patch features. And so all these different data sets can be fed into an image classification algorithm to sort of define what the vegetation is. But one of our first things with, and I'll get to that here in a second, of how we classified this stuff. But one of our big things with BLM is looking at how we can compare our UAV classification to their AIM classifications. And so what they do is they go down, they spread out a transect, and they do point line intercepts where they drop a point off the transect every 50 centimeters, record the vegetation, and then every 250 centimeters they record vegetation height off to the side of the transects. So obviously mapping, taking UAV data that's in 2D and applying it to a 3-dimensional ground surface, it's not as easy as just dropping points on the line. So we had to develop a workflow to basically make our observations down our transects equivalent to what a 50 centimeter would be on the ground. There's a built-in add-on, an arc, that will allow you to measure distance along a 3-dimensional line, but it only works in integer values, so you can't use 50 centimeters. So we ended up having to split the transects at the midpoints, or add points every meter, and then split the transect along those points, and then add a midpoint. So you're basically inferring the middle 50 centimeter point across each meter, but given the landscape is pretty flat, it should be a reasonable and close enough to their draped tape measure. So the next thing we did was calculate vegetation heights. And so we did this again in PhotoScan using their classified ground point feature in the dense point cloud. So here's our dense point cloud. You can classify all the ground points by adjusting some parameter values. It was a very iterative process to figure out the best methods to keep small vegetation being classified as not ground, but not losing crown height. And then so what you do after you've classified your ground surface is you develop a DEM from all the data points, and then you develop a DTM by just classifying, by building a digital terrain model just from the points that are classified as ground, and this interpolates through all of your vegetation points. And so you can see in this plot we lose all of our vegetation, and then using a raster calculator you can subtract the DTM from the DEM, and it gets you a vegetation height model. And then so we can now look at this vegetation height model down our transects. And so you can see this is an AIM plot that has 3 transects. The north transect, you can see the yellow and red lines are the actual DEM model. So that's what the actual land surface is doing, where the gray and blue lines are what the vegetation surface is. So each peak in the gray and blue lines represents an individual plant along the transect, so we can now classify veg height and compare that to what BLM's field survey crew was doing. You can see it looks to be doing pretty well. We were obviously identifying the big, long, flat, open expanse in the north transect, picking up a lot of the bushes in the southern transect. And so now the big challenge is doing the image classification. And so for our time series flights, we ran an unsupervised ISO classification from just a single flight using the NDVI, the height metric, and a texture metric, so the standard deviation of a given neighborhood. This produced 21 classes. This was all done in ARC. And then by visually inspecting these classes, we were able to collapse that down to 6 different vegetation classes. And then so we added the other 8 NDVI layers and then ran the same classification. This produced 27 classes, which collapsed down to 9 classes. These additional classes are not actually different vegetation classes, but they're different phenological groups. So, for example, sagebrush that senesced later, or grasses in this draw. You see the draw north of the road. Those grasses stayed greener longer than their stuff, so we were able to pull out phenological differences between different functional groups within the area. But we found that the multiple flights really improved classification by adding in all data from all flights as opposed to a single classifier. But we did still see a lot of pixel mixing, especially between soil and litter and sparse herb and sage and dense herb. But as I said, we were able to pull out like temporal NDVI for different classes. So this is what the NDVI curves look like for each of our 9 classes over the growing season. So notice you can see, obviously bare ground has a pretty consistent NDVI curve. Same with litter. But if you start looking at the different herbaceous groups, you can see sort of the short-term and long-term growth in their NDVI curves. So our next step with this is to look and see how each functional group is affecting the output from a MODIS and Landsat pixels. And so now for classifying the landscape flights, so we now only have a single time step. We've covered a lot more ground, so we have a lot greater habitat heterogeneity. So we're looking at adding additional variables than we use in the time series. So again, the time series was NDVI, veg height, texture. We're looking at adding false color, infrared, maybe some additional ones, maybe using straight RGBs, and looking at some additional vegetation classification approaches. So we've looked at a few so far. On unsupervised approaches, we looked at ISO cluster like we did for the time series, a K-means clustering, and then in the supervised world, we've started down some random forest models, and then we'd like to start looking toward object-based analysis, sort of maybe a segment mean shift approach. We haven't gotten there yet. So now I'll just give you some examples of what this classification looks like using different models. So here's our ISO cluster. Here's a site in Billings, and so you can see the zoomed in area down low. The ISO cluster is doing okay, but we're not able to. So this is, I should step back. This is a clustering algorithm where you have really no control of what's getting pulled out. It's unsupervised. So you basically feed it the data sets, and it tells you what it finds that are similar based on the different variables. And so you can see it's doing a decent job of pulling out the bare ground, but it's linking a lot of that with litter, and it's clearly a shadow class that it's pulling out. And this is just a switch to what the false color image that it was looking at from the MicaSense. So K-means probably our worst performing model. It seems to be really affected by height and losing a lot of variance in the smaller vegetation. Everything's getting washed out into one class. Our random forest model has a lot of promise. It's doing a better job of pulling out litter. So this is a supervised classification approach where you basically feed it training data. So you go through the image and you draw polygons over the different features that you want it to learn on and train on. And so we fed it, bare ground. We fed it sagebrush. We fed it some of the higher herbaceous cover, litter. And so it does a pretty good job of pulling out these things. vegetation height seems to be really affecting all of these models. A lot of the stuff starts to get like banded up by height, and so we're playing with the idea of maybe masking our trees out. But here's really promising. This is just a random forest from just the ricoh only, and sort of ditching all the MicaSense data. And this had probably our best classification that we've seen. And so, like I said, we're still tracking down this road and looking at that. So here's another random forest from a different site. You see it's really able to pull out the bare ground and the grasses and the draw. And so our next steps are do the vegetation height comparison. We've got the workflow developed for how to identify where they're actually measuring on the ground and the data sets from BLM now, but we haven't had a chance to validate this. We need to finish our vegetation classification and potentially look at other thresholding metrics after our classification. Like I said, the height is turning out to be really problematic, and so maybe there's a way to reclassify pixels based on height or other thresholdings post-classifications. Still need to do an analysis looking at maybe some object-based image analysis approaches, and then obviously do our comparison with Landsat models to see how our models are comparing with what is being produced from BLM's Landsat models. And with that, I'll take any questions you guys may have.
Great, thanks, Todd. Questions for Todd? Well, I've got a question. What are your thoughts on classifying the vegetation heights using MetaShape?
That's what we did. We did it all in PhotoScan. But what we need to do is we need to compare it to what BLM is trying to do, if I heard your question right.
Cool.
Because that's our big model comparison, right? So for BLM, one of their major components is sagebrush height for their habitat mapping, and so we need to have confidence that our MetaShape produced height is actually correlated with what's on the ground. Because oftentimes these vegetation classification approaches or veg height classification underestimates height, and so if we can find like a global parameter to adjust ours, if we have enough sample size, see what's actually coming from the UAV versus what's being measured on the ground.
Awesome. Got a question online. Do you think the better classification of the ricoh data versus the MicaSense is primarily a function of the difference in resolution between the different cameras, or do you think it's something else?
I'm not really sure. And we fed it a lot of different variables with the MicaSense, and I haven't done just a single random forest of maybe just the RGB from the ricoh, but actually a lot of this stuff, the smaller pixel size is actually a detriment, because if you're doing a training algorithm and you're taking a polygon of sage, right? So imagine looking down on a sagebrush, you're seeing a bunch of leaves, some stems, interstitial spaces between that. So the smaller the resolution, the more variance there is in the pixels that it's trying to train on. So that's why as pixel size goes down, you start shifting to object-based approaches. But I'm not sure how much of it is a pixel size thing or the different variables that it's getting fed.
Excellent. Another question online. Did you perform an atmospheric correction on your MicaSense data?
Yes, we did.
Excellent. Another question. Do you think that the MicaSense imagery will serve as a better comparison to the Landsat data based on its extension of spectral sensitivity into the near-infrared bands?
We're hoping so. I should probably step back. What they do with the Landsat model is they're trying to basically pull out, percent sage, percent bare ground, say, percent rock, herbaceous grass, and so we're really more trying to pull out a vegetation classification model that we can basically develop those same metrics and compare it to what's getting spit out at Landsat.
Excellent. Someone would like you to go back to your graph of NDVI and the DOI and explain the graph just a bit further?
So the plot on the left is a comparison of our MicaSense data to MODIS and Landsat. And so you can see that it's a single MODIS pixel, that's why there's no error bars on it. And then the bars are standard deviations of pixel values. And so you can see that we're seeing a very similar phenological signal between the MicaSense data and the two satellite data sets. But then once we classified our data into our different vegetation classifications, we can then just pull NDVI values based on those subset of pixels. And so what we can look at is sort of different phenological responses over the growing season. So we found look at the bottom two plots on the right there. So you see there's a short duration sagebrush and a long duration sagebrush. So even though these look very similar in all your RGB values, height values, but what we're seeing is a different NDVI curve for these long duration sagebrush. So they were staying greener longer and be more productive, and those often map to areas of the habitat such as a draw or someplace else that has more runoff or more groundwater. And we also see that with the sort of the herbaceous groups as well. And so what we're trying to look at now with the Landsat and other stuff is how much each functional group is influencing the overall NDVI value that's coming off of a much larger Landsat pixel, which is 30 by 30 meters. And MODIS, I should have said, is 250 by 250.
Excellent, Todd. Another question wants to know if you were, what were you using to calibrate your reflectance panels and how many?
We just used the standard panel and took 2 or 3 pictures before and after each flight.
Good. So you followed the MicaSense suggestions. And then along the same lines, are you putting down ground control points? And if so, how are they surveyed into your study?
Yeah, so we put a ground control. So this was trying to make it like a programmatic field level approach, which is, so we went with non-arrow point targets. We just had targets, you can kind of see so we had targets like this. We had one at the plot center for BLM's aim plots and one at the end of each transect. So once we had our imagery, we could just we'd put a point down on each target and draw a line between the points so we knew where their transect went. And then we also had 4 points on the edge, basically each corner of our 300-meter grid. And then when we went to, we just surveyed those in the field with a handheld GPS with an accuracy of about 3 meters. And so when we aligned our stuff, we only used the 4 targets on the edge and then 1 in the middle, so we didn't cluster our error around the transect area. The registration error for Landsat is about 8 meters, so our error is about half or less than half of a Landsat pixel. So in terms of that comparison, we're well within the error margin.
Very good. Mark Bauer responded online, just a comment. There's a extraction feature in Global Mapper that will pull height above ground values from the point cloud. It might be fun to compare those values with that tool set. And Todd, he sent you a link so you can talk about that some more. And
okay.
Building onto that.
I assume that's the same kind of approach though, right? You have to classify what's ground and what's vegetation.
Yeah, I'll have to let Mark respond to that. Along the same lines, Global Mapper also has canopy height stuff. It's a great tool for post-processing and some suggestions on that as well. Mark, did you want to respond?
Yeah, can you hear me?
Yep.
Yep.
Yeah, you can actually, I recommend classifying the ground first so you can get accurate height above ground values, but you can also run it and it will, without classifying the points, and it'll come up with the best estimate for it. So you could probably run it a couple different ways, Todd, and check it out. But I thought it'd be interesting to do a comparison based off your subtraction method and see what we're getting.
Yeah, no, that'd be really interesting.
Cool.
These height seems to be really good for classifying, especially sage, but once you start getting into trees, it really starts to mess everything up because it's trying to basically band it out. You get these like weird classifications that go up a tree.
Yeah,
and obviously height's driving that model.
On the features, because you can get multiple points too for, you know, it might try to find a tree height in the multiple regions. So just some things to think about.
Yeah, well, thank you.
Excellent. Those are good points. Any other questions for Todd? That's a great presentation, Todd. Thanks for sharing that with us. And we look forward to finding out some more results once you get the rest of the stuff worked out.
Hey, Todd, Joe Adams. Hey,
Joe, we can hardly hear you, Joe.
Oh, how about now?
Much better.
Yeah. Hey, Todd. Hey, back to your atmospheric correction question. What method did you use for the atmospheric correction?
I don't know. Like, we didn't do an atmospheric correction. We just used the upwelling light sensor.
Yeah,
that's what they meant.
You used the MicaSense calibration panels, right?
Mm-hmm.
And yeah. Okay. So yeah, Carrie Middleton asked about atmospheric correction, and I just wanted to clarify that is a different process, I think, and unless Carrie is there and can talk, I assume she's thinking atmospheric is a different thing than the radiometric calibration, but I'm not sure.
Good points. Good points.
Carrie, yeah, the reason I brought up the atmospheric correction is because you guys were using the NDVI to kind of look at the different functional groups. And so depending on, you know, the different methods that are used for atmospheric correction, I mean, there's some that are end scenes, there are some that are dark object subtractions, and that could kind of affect a little bit of the results for some of what you might delineate as feature areas for those functional groups. That's all I wanted to say. I mean, it's a different thing, you're right, than the radiometric panels, because that's the radiometric calibration. And that's a different process, like you said, that's different than the atmospheric correction part.
Yeah, let me like this. So there's enough, or maybe I'm still confused, but there's the upwelling light sensor that's looking at the incoming solar radiation, and so we're applying that correction. But that's are you talking about like a different correction than that? And,
yeah,
pulling
and,
like
I mean, you know, because you got to account for the water vapor in the air, dust particles, and other things. You know, just for being able to repeat the same kind of, like if you go back to the site in 2 months, you know, and then the phenology of the vegetation will be very different, but you want, you know, to still have the same results for your functional area as your functional group.
No, and I think we see that in the, you know, so if you look at just these plots, right? So even something like bare ground, so these are the same pixels being classified over and over, but we're seeing a pretty
similar trends. So that's probably what you're more after, is the trending rather than the actual pixel value each time, right?
Mm-hmm. But we're seeing still quite a bit of variance in what the NDVI value is for the same group of pixels over time, and in something like bare ground, that should, you know, be very minimal. And so I wonder if the atmospheric correction would help change that out.
Yeah. And the other question I had was, you know, whenever you guys were doing the transects with the three-dimensional distance, you know, the ground following distance, are you doing that in ArcGIS Pro?
Just desktop, but it's the add-in. I've messed around with it in Pro, and it's the problem is the add-in doesn't allow you to look in non-integer values. It works really well. I spent actually a couple of days digging around because it's obviously a major problem. And if you have anything that works in Pro better, that'll allow you, because basically you're just draping you draw the transect and then you drape it over the DEM, and so then you get the three-dimensional line, and then you want to measure along the three-dimensional distance, because that's what their tape measure is doing on the ground. At every 50 centimeters, you get a point.
Yeah, for the vegetation height stuff, I mean, I thought that graph was really useful and very telling, you know, and that's why I was kind of asking what you used to do the overtrain measurement with.
Great. Thank you, Carrie. Another question online, Todd. Can you address why the vegetation height models tend to underestimate the vegetation height?
Yeah, so you got a 3 centimeter or 1 centimeter pixel, right? So the small little top of a shrub or a bush sticking up, that's not really big enough to be a pixel. And so when you're on the ground and measuring it, you can easily measure that value. But in an image with the pixel size, right, it has to find enough objects or enough space to make a pixel. And so you lose a lot of the actual height of the small shrubs and bushes, like especially grasses. It's really hard to get a UAV-derived grass height from like the sparse bunch grass because there's just not enough, pieces of the grass in a pixel.
Great points. Those are excellent. Any other questions for Todd? Oh, there's one just popped up. Do you have a sense of when the vegetation height comparison model no longer works well because of the canopy closure? Basically the height between the DTM and the vegetation tops?
I'm not sure I'm following. Can you read that again?
Yeah. Do you have a sense of when the vegetation height comparison model no longer works well because of the canopy closure? So basically the height between the DTM and vegetation tops.
I don't.
That's fine. You could say that.
I guess obviously the more. Actually, I think I know what you're talking about. Now I think about it. So yes, in South Dakota this year they had a ton of sweet clover, which basically grows at like a kind of monotopic height, and it can cover big areas. And so yes, once you get into the center of the patch, the vegetation height model out there kind of fails because there's no longer the way that Metashape is looking at this. It's looking at neighboring pixels or neighboring points in the point cloud and trying to look at variance between them. So what's the angle between them? What's the height difference? And so once you get into a big patch of vegetation, it's going to start failing. And I don't really have a sense of, you might be able to adjust the parameters settings to look at like a larger patch, but it does start to fail, at least from what I've seen. Once you get anything kind of deeper than 2 or 3 meters in an area, it sort of stops classifying.
Excellent. Thank you, Todd. Any other questions for Todd? Once again, thanks for presenting before us this month, and we appreciate it very much. I'll wrap up the meeting. We're getting close to our time here, but I appreciate you taking your time with us today. Just a quick reminder that our call next month will be on March 4th at 1 o'clock Eastern. And reminder, our calls are the first Wednesday of the month. And I went ahead and put the dates for the upcoming calls. Note that May 13th will not be the first Wednesday of the month due to another scheduling issue, but certainly we all have a lot of questions regarding DOI, UAS, and like I said, we're going to try and get that information out to you as quickly as possible when we get it. Certainly would echo Brad's comments in sending questions up within your Bureau leadership, because right now seems like the Bureau leadership is really where the action is going to occur. And I think that's going to conclude what we have for you this month. Thanks so very much, and we look forward to seeing you next month.
Hey, Todd, lots of thank yous in the chat. Thanks a bunch.
Thanks, Joe.